Today we continue the session on electric circuit elements and we discuss the interconnections between the essentially sources and some of the elements as also. Okay, because when we have interconnected sources, the interconnections have a big role to play, and the nature of the source is also going to have a bearing on the loads that are connected to that. Okay, so the interconnection is an important aspect that also needs to be studied. Okay, of course we have studied quite a large number of interconnections, and in problem one also we have a different kind of interconnection. That's all. Okay, we have several sources here, but I hope you observe that when you are having a 200 volt source in series with a 50 ohm resistor, the maximum current that is possible, okay, if you have short circuit in the terminals, is equal to 4 amps. We have a similar situation also in the 100 volt in series with 25 ohm source given alongside. Okay, so one next to it. Okay, a little next to it. Okay, so there of course the directions are different, so we have a circulating current. Okay, so this is the speciality of circuits. We can see that there's a circulating current element there, wherein the current that goes up through the 200 volt source comes down via the 100 volt circuit. Okay, because the resistors and the sources match. Okay, there's a similar situation is also there for 160 volt in series with 40 ohms when compared to the 80 volt and 20 ohms, where the sources are back to back and we have the same kind of circulating current there, which means that there is no current that is left for flowing through the 20 ohms. Okay, because the two terminals are the same potential, and that's exactly what is asked, the current I flowing the circuit shown below in armature race. Okay, so we have several batteries set up such that there are circulating elements there and nothing is left for the 20 volt source, 20 ohms resistor, because both the potentials happen to be at the same potential. Okay? Both the nodes. Okay? Moving on to problem 2, where quite a large number of ideal sources are shown. So if they are delivering power, they can be sources. Otherwise they are circuit elements. Okay, perhaps they are getting charged. So it's like just like a battery getting charged and behaving like a load. Okay, so what is asked is what's the ratio of maximum power consumed in an element. Okay, so if it is consuming power, then the voltage and current directions will be opposite to each other. Okay, on the other hand, to the minimum power delivered. Okay, so when it's delivering power, both the directions will be the same. Okay, by an element in the given interconnection sources. Okay, so we see that the 10 ampere current source and 5 ampere current source together deliver 15 amps to the 100 volt source, making it a consumer. Okay, it's consuming the voltage and current are in opposite direction of a consumer of 1500 watts. Okay, the 10 ampere source on the other hand now delivers. Okay, because 10 into 100. Okay, 100 volt is across it. It delivers 1000 watts. Okay, the 5 ampere source has the 100 plus 40, 140 volts in the same direction. So it is also delivering power as given by 5 into 140, 700 watts. Okay, and for the 40 volt source, we have current and voltages in opposite direction because the 5 ampere flows in the opposite direction. So we have 200 watts there. 200 watts being consumed. Okay, so the largest consumer is 1500 watts, and the minimum deliverance is of 700 watts by the 5 ampere source. So 1500 by 700 is the ratio that is required out of us. Okay, moving on to problem number 3. Here we see an AC source feeding a series element of R and C, and also a shunt element where R and C are the same old R and C are in parallel. Okay, and what is the problem? The problem says that the circuit shown below is driven by a sinusoid voltage input VI is equal to VP cos T by RC. Here more focus on has to be given to omega, okay, which is equal to 1 by RC, because it has a bearing on the load. Okay, and VP is the magnitude. Okay, so the steady state output voltage V0 is what. Okay, so now that we have got omega, we can convert the capacitance to its reactance as given by 1 by omega C. So 1 by RC, and C is there, and minus J. So it is the same as equal to minus JR. Okay, so now we have a series element of R and minus JR, or R minus JR, and we also have the same R and minus JR in parallel. Okay, because capacitance reactance is equal to minus JR. So when R and minus JR in parallel, it is the same as equal to R into minus JR divided by R minus JR, multiply and divide by R plus JR, tells us that that's when R and minus JR are parallel together, the effective impedance is equal to R minus JR by 2 or R by 2 minus JR by 2. Okay, if, on the other hand, if it was inductive reactances which are being parallel, then it would have been R plus JR by 2, as simple as that. Okay, so now we see that the voltage is now feeding a potential divider. The series branches R plus R minus JR by 2, sorry, R minus JR, and the shunt element is R minus JR by 2. Okay, so it is a division of voltage in the ratio of half is to 1 plus half or 1.5, or it is so the voltage magnitude is going to be divided to one third its value as the output, and the angle is not changing at all. Why? Because both the numerator and the denominator have the same angle. Okay, it is going to be 45 degrees. Okay, so we see that the answer is A, Vp by 3 cos t by Rc. Okay, there's no change in angle, it doesn't become sine. Okay, moving on to the fourth problem. Here, what all do we observe? We see first and foremost 6 and okay, we see a current source and a voltage source. Okay, and the current source is in parallel with minus J3. Okay, that's good. And the voltage source has a resistance across it, which we discard, because any impedance directly across a voltage source can be removed from analysis. Okay, and now we also see that 6 and J6 are in parallel. So immediately it comes to us that it is the same as equal to 3 plus J3. When you see 3 plus J3, we try to remove minus J3 from the situation. How? By giving rise to a voltage source. Okay, so what's the voltage source? It is the same as equal to minus J12, and the minus J3 comes in series with it. So now we are having a total voltage in the circuit as given by my 10 minus J12. Okay, so as given by minus 10 minus J12. If you look at the reference, it is the minus 10 minus J12. Okay, and then that is going to be divided by the impedances in series, which are 3 plus J3 and 3 plus J3 and minus J3. Okay, so what's the net result? It is going to be minus 10 minus J12 because of the directions into 3 plus J3 divided by 3 plus J3 minus J3 or 3. Okay, it's going to be 1 plus J multiplied by 10 minus 10 minus J10. So the answer is automatically very clear and is as given. Okay, so moving on to the fifth problem, we see that we are having a capacitance and a network of resistances connected to a 10 volt sources. The grounded terminals are shown, and it's a DC source, which means that the capacitor is going to open out after getting charged, such that the entire voltage gets dropped over it, obeying Kirchhoff's voltage law. Okay, the resistor network tells us that it's a Wheatstone bridge, so the center 5 ohm can be removed, and so now we are having 10 ohms and 10 ohms in parallel because of the grounded terminal, so it's 5 ohms. Okay, so with this information, let's read the problem. The initial charge in the 1 farad capacitor present in the circuit shown is 0. Okay, the energy in joules, okay, transferred from the DC source. So energy is both for the capacitor as also for the resistors, so long as it is active. Okay, so long as current flows through it. Once current does not flow, there's no energy stored. Okay, until steady state conditions reach. So steady state voltage is 10 volt across the capacitor, so it's half CV squared, that gives rise to 50 joules. Okay, and now looking at the happenings in the resistive network, it is having a current as given by 10 by 5. Okay, when the capacitor was shorted right at the beginning, so 10 by 5, which is 2 ampere square, and then the current was decaying down, and it is given by e raised to minus t by RC or e raised to minus t by 5. Okay, now you have to square the current. Okay, and then integrate it with respect to time, right, multiplied by the resistor to give us the energy. So we have 5 into 10 by 5 is squared to become 4, and then e raised to minus t by 5 is now squared to become e raised to minus 2t by 5. Okay, so integrated. So you see that that minus 2 by 5 comes on the denominator, but at the same time, since you are integrating from 0 to infinity, you see that you get a minus 1 also there, and so ultimately we see that the resistive component also absorbs an energy of 50 joules from the so still it is depleted, or the capacitor brings about an open circuit. Okay, moving on to problem number 6. Here we see that we are having 3 perhaps generating stations each giving rise to some power being generated. Okay, and there are equal impedances connecting them on either, connecting the central station to either sides. Okay, and what does it demand? In the figure, the voltages are V1t 100 cos omega t. Okay, so 100 cos omega t, the magnitude 100, and the cos omega t being reference has been put on the base there. Okay, in the diagram shown alongside. Okay, equal to and V2 equal to 100. Okay, so the magnitude is the same, but cos omega t plus pi by 18. So it's all this, it's the same old cos. So you can use the same base, but you have to give an angle lead of 180 by 180, 180 by 18, that is the 10 degrees. Okay, so V2 is also shown there with the 10 degrees lead, exaggerated of course. Okay, V3 is now 100 again, magnitude, but cos omega t plus pi by 36. So which means only 5 degrees of lead is there. So V1, V3 and V2 are appropriately shown in the diagram, which gives us the understanding for following further. Okay, the circuit is in sinusoidal steady state and R is very small. So we're quite very little of consumption is happening there, but perhaps the stations are being charged. Okay, because not all can generate energy. Some will be generating, the others will be consuming. Okay, so P2 okay, R is very much smaller than omega L. Okay, and of course the currents will be having a 90 degrees, near around 90 degrees of lag as well. Okay, because the circuit is essentially inductive in nature. P1, P2 and P3 are the average power outputs. Which one of the following statements is true? Okay, so as I said earlier, whatever is consuming will have a negative power, and which is less than 0. If you look at the answers, you see equal to 0 and less than 0, etc., or greater than 0, etc. So let's have a look at that. Which one of the following statements is true? Okay, so let's see. We see that. Okay, so there are two aspects to see from where the power is generated or which delivers the power. Okay, so we see that the one aspect is that the magnitude of the voltage should be larger. Okay, and okay, in this case all the magnitudes are equal. So now we come to the second aspect. Second aspect is that whichever is leading the rest in an AC circumstance, when you are having a leading voltage, okay, with the equal value, that is the source. Okay, or from where it is from here that the power flows. So definitely V2 indicative of station 2 or P2 is positive. Okay, P2 is positive and the other two are lagging V2, so they are both consuming power. Both V3 and V1 are consuming power. So we should see that P1 and P3 should be less than 0 and P2 should be greater than 0. Okay, so answer 3C seems to be the most appropriate answer for it. Okay, so let's come to the last of the sessions, the last of the problems in this session. The old problem that we had discussed earlier is now taken here, and what is asked is they evaluate the power delivered by the 10 volt source, whatever, be it 10 volt or a 2 ampere source. Okay, we can do this problem. Okay, so how do we do this problem? Okay, so here another technique has been done, wherein we see that we are having the 2 volt source in series with the 2 ohm resistor has been converted to a 1 amp source with a 2 ohm resistor, giving rise to a delta with delta constituting the 4 ohm and 6 ohm, and that delta has been that delta has been converted to a star equivalent with 2 by 3, 2 and 1 as shown in the figure given alongside. Okay, so now now it's easy to solve because we can say that a current I flows through 2 by 3. Okay, and 2 amps joins it, and then together they flow to the 1 ohm, and then 1 amp also joins it, and so we have a current flowing through the 10 volt source, and so we can see the power developed by the 10 volt source. Okay, so now we see that. Okay, so now let's substitute there 12 minus 2 by 3 into I. Okay, minus 1 into 2 plus I is equal to 10 volt. Okay, so from one end to other end. Okay, so we see that in this case I is equal to 0 or no current flows through the 2 by 3 ohms. Okay, so it can as well be removed. Okay, so now we have 2 amps coming to the junction, coming to the 10 volt source, and 1 amp also joining it. So 3 amps together comes to the 10 volt source, giving rise to 3 into 10. But of course the directions are different, so it is now going to consume the power as given by 3 into 10, 30 watt. Okay, so that's all for today. I hope that circulating currents can be set up, And when there are interconnections, it's clear to you that that when we have an interconnection together, the total power will be equal to zero. But some of them will be, even though they are sources, some of them will be charged and some of them will be discharging the power required by the batteries which are being charged. We also saw very important understanding that we can take to any context, which is that when we are having an inductive reactance or a capacitive reactance of equal magnitude with respect to a resistor parallel together, then the total becomes equal to R plus J by R plus R by 2 plus J R by 2 if they are if it is an inductance. Otherwise it becomes R by 2 minus J R by 2, which is very important. And we can always go in for source transformation such that some cancellations can occur. We also saw that any impedance connected directly across a voltage source can be removed for the analysis purposes. We also saw that the current flowing through a resistive network when it's connected to a capacitor which is going to open out soon enough is given by the value at the beginning, which is equal to V by R multiplied by e raised to minus t by RC, and this is going to be squared and then and integrated with respect to time to get the joules equivalent, and of course multiplied by the resistive component. Okay, so all those things we saw. And we also saw that whenever the voltage magnitude is larger than the other magnitudes, then that is going to be where from the power is going to flow. And if not the magnitude, the angle of lead also gives rise to a situation wherein the power source is going to be the station which is running at a lead power angle. Okay, so finally we also saw the importance of source transformation, and source transformation giving rise to more and more clearance from the insides of the circuit such that we can solve the problem in a much easier manner or with less cluttering.